So, chapter 6 brings us to chemical reactions and equations. And so, in this chapter, we'll be talking about how to read and how to use chemical reactions and the equations and to determine information about the reactants and the products of the reaction. So we up to this point we've been leading up to chemical reactions because we already talked about chemical changes. And so a chemical change, if you remember, is when a substance is changed into a new substance. So we have one or more substances, and they have some type of chemical change brought upon them, and they're made into new materials, made into new substances. And so we can observe these chemical changes by seeing maybe a change in color, or maybe we see a change in physical state, either um, adding two liquids together and getting a solid or something along those lines. Sometimes we may see the formation of bubbles, so we might see some effervescence and seeing bubbling going on. And so many of these things are evidences used to prove that there was an actual chemical reaction undergone. Another one that we didn't mention was sometimes when you add materials together, those substances may produce heat, or they may absorb heat, so they may feel warm or cool when they react together. So when we talk about chemical reactions, a chemical reaction involves the arrangement of atoms. So we're going to um, see a new arrangement, a new combination of atoms put together. And that's the arrangement of atoms is basically if we have a compound or molecule, and so if we rearrange them, we're going to have new compounds and new molecules. So in the chemical reaction, we're going to produce one or more new substances. So um, sometimes we have materials combined into one new substance. Sometimes we have materials break apart into new substances. Sometimes we have just new substances, coming together and making totally new ones. And so we have any one of those types of reactions, and later on we'll talk about the different types of reactions. And so when we have these types of reactions, they usually can be observed by the appearance of new physical properties. So like we said, a change in color or a change in physical state and things along those lines. So when we are writing a chemical equation, we have several parts of that chemical equation, and we need to be able to understand what each of these parts are. And so the materials that react together are called the reactants. The reactants react together. And then the products is what you produce or what you make. So the reactants start usually on the left-hand side of the chemical equation, and you'll always have the arrow starting in that direction, on that side. And then the arrow is going to point toward the products, because that's where we're moving toward. We're going to be moving toward the products. That's what we're going to make. That's what we're going to produce. And so the products will be on the right-hand side of the reaction or equation. When we have more than one material reacting together or made, we use a plus sign. So in this one, we have carbon plus oxygen. So that means that both carbon and oxygen are reacting together, and those are the two reactants. In this equation, we see a triangle on top of the arrow. That triangle represents that heat is needed for this reaction to occur. We also see these letters in parentheses, and these letters indicate the physical state of the materials, of the substances. And so S is for solid, L is for liquid, G is for gas. And then a lot of times we also use what we call aqueous, and that just means it's dissolved in water. So aqueous comes from aqua, and we're going to have a lot of reactions take place in that with materials that are dissolved in water. And so AQ is used to represent those. So here's just a picture kind of showing the reaction and showing what's taking place. And so here we're using natural gas or methane and using it to produce fire. And so what we have here is the methane gas comes in, and it also requires oxygen to produce that flame. And so those are our two reactants. Those are what we need. And then it's going to make, after those two burn together, those are going to make carbon dioxide and water. And so the carbon dioxide and water are moving out, and those are our products. So when we write out chemical equations, it's very important that they are balanced. And so when a chemical equation is balanced, that means that we have the same number of each type of atom in both the reactants and the products. And so if we look at this example here, we have hydrogen gas reacting with oxygen gas and producing water vapor. And so here we see that we have a what we call a coefficient in front of the hydrogen gas, the H2. And that 2 in front of the H is distributed to everything in that molecule. And so since it's only the hydrogens, then that 2 is only distributed to that hydrogen. And then if you remember the subscripts are belong to the atom that it's following. And so here we have to multiply 2 with the other 2 to have 4 hydrogen atoms. And so we have those 4 hydrogen atoms, and then we also have O2, and so the 2 belongs to the O, and so we have 2 oxygen atoms, and that's all in the reactants. And then we have 2 H2O in the products. And so again, here we see another coefficient of as a 2 in front of the H2O. And so that first 2, that large 2 in front of the H, is distributed to both the H and the O. And so we have 2 hydrogens in H2O, and then we have 2 molecules of H2O, so it's 2 times the 2 for the H, and so that we end up with 4 hydrogen atoms. And then that 2 is also distributed to the O in H2O, and we only have one O in H2O, but we have 2 molecules, and so it's 2 times 1, and so we get 2 oxygen atoms. And so that number that's placed in front is what we call, again, is a coefficient, and so that's distributed to that whole molecule or whatever it's in front of. So it's very important that you check to make sure that the reactions are balanced. And so one technique that is used is to write out a table. And so you can just list out all the atoms that are found within the chemical equation. And then you can have a column for reactants and a column for products. And so you can just, follow along on both the reactants and products for each atom and see if they are balanced. And if not, then work must be done in order to balance them out. And so when we are balancing the chemical equation, these are just some guidelines that you can follow. You want to first write out the equation using the correct formulas for the reactants and the products. So just write out the reaction, basically. And just making sure that you have the right chemical formulas. Second one is you want to count the number of atoms of each element in the reactants and products. So you make that list out in that table and figure out how many of each atom you have in the reactants and in the products. And if they are not balanced, then you can add coefficients in front of a molecule in an attempt to balance out the elements. And so we're going to show how that's done and work out some examples. And then lastly, you can just do a final check to make sure that it is indeed balanced. So here is a question. We are burning ethanol in the presence of oxygen gas, and we're going to produce water vapor, steam, and carbon dioxide. And so here we just want to make sure that we write out the chemical equation in a proper way. And so we're starting with ethanol and oxygen. That's what we're going to react together. And so that goes on the left-hand side of the reaction. And then we're going to produce water and carbon dioxide. And so those are our products. And so that's what we're going to make. And that's going to go on the right-hand side of the chemical equation. Next thing we want to do is we want to make that table, list out how many of each atom or element we have and the reactants and the products. So on the left-hand side, we have carbon, and the only source of carbon is the ethanol, and it says C2. So we have 2 carbons on the reactants. And then if we look on the right-hand side, the only source of carbon is CO2. So that's 1 carbon in the products. Then we see that we have our next element is hydrogen, the H, and so our only source of H on the left-hand side is the ethanol again, and we have H6, so we have 6 hydrogens. And then we're looking on the right-hand side, we see that we have only source of hydrogen is the water, and so that's H2, so 2 H's. And then we have oxygen. And so on the oxygen, on the reactants, we have the oxygen in both ethanol and in the oxygen gas. So we have 3 total oxygens in the reactants. And again, on the right-hand side, we also have 3 oxygens, 1 in the water and 2 in carbon dioxide. So it's not balanced, but we have everything written out, and so we know it's not balanced, and so we know we have some work to do. So next thing we want to do is just try to figure out the combination of coefficients to use in creating a balanced reaction. And so this takes some work and this takes some practice in doing. And we'll show a couple in the workout problems. And so just to verbally go through it, what I would have done is I would have first balanced out my carbons. I noticed that there was 2 carbons in the reactants and only 1 in the products. And so I would have first have just balanced out the carbons. And so in order to do that, I would have to put a 2 in front of the carbon dioxide. And so then my carbons would have been balanced. All right, and so we would have 2 carbons on the reactants and 2 carbons on the products. Then I would have done hydrogen, because hydrogen is only found in one place on the left and only found in one place on the right. And so we had 6 hydrogens on the left, and so we need to get 6 on the right, and so you would have to add a 3 in front of the H2O. And so that would bring the 6 hydrogens on the products as well. And then we want to just make sure that our oxygens are still balanced. So we still have 1 from the ethanol and the reactants, and then 3 times the 2 for the oxygens on the reactants. So that would be 6. So 6 plus 1 is a total of 7 oxygens in the reactants. Then for the products, we have that 3 in front of H2O. So it's 3 times 1. And then we have the 2 in front of the CO2. So it's 2 times 2, which is 4. So we have 3 from the water part and 4 from the carbon dioxide part, which is a total of 7. And so we have 7 on the left and 7 on the right. And so we get a balanced chemical equation. And so here it's just we need to determine if the equation is balanced or not. And so here we can see that we have 1 sodium on the left and 3 on the right in number 1. And so obviously we already know this is not balanced. And then you can also just double check. We have 2 nitrogens on the left and only 1 on the right. So not balanced in 1. And then 2. We have C2, so we have 2 carbons on the left, and then C2, 2 carbons on the right. Hydrogens, we have 4 from C2H4, and then 2 plus H2O, so that's a total of 6. And then we have C2H5OH, so that's a total of 6 as well. So 6 on the left, 6 on the right. And then we have 1 oxygen in the reactants in H2O, and then 1 in the ethanol, C2H5OH. So that number 2 is indeed balanced. And so here, just showing all the steps out in number 1. And so just writing out that table, and we just have to answer if it's balanced or not. We don't actually balance it in this part. Number 2 is done in the same way. You just list out the atoms in the reaction, and then figure out how many of each you have on both sides of the chemical equation. And so this one was balanced. So here it's asking us to write a balanced equation for the reaction of nitrogen gas and hydrogen gas to form ammonia gas. And so we'll just kind of go through and explain the steps. So we want to make sure first we want to write the chemical equation. So the first thing we want to look at is what's reactants, what's the products. So you have a reaction of nitrogen gas and hydrogen gas. So that's going to be our reactants. It's N2 and H2. And we're going to form ammonia, NH3. So that's going to be our product. So the reactants, the N2 and H2, go on the left-hand side of the chemical equation. And then the NH3 is what we make. So that's going to be a product. And that goes on the right-hand side of the chemical equation. Then we just need to see if it's balanced or not. And so we list out all the atoms, element types that we have. And so we only have to deal with nitrogen and hydrogens. We have 2 nitrogens on the reactants and 2 hydrogens in the reactants. And then on the products, we have 1 nitrogen and we have 3 hydrogens. So we are not balanced. So we're not balanced, and so we would have to add coefficients to balance out this chemical equation. So the first thing I would have done was put a 2 in front of the NH3 to balance out my nitrogens. And so in doing that, that 2 gets distributed to the N and the H. So that brings the hydrogens in the products up to 6. And so we need to go back and then balance out the hydrogens. And so in order to balance out the hydrogens, you need to put a 3 in front of the H2 in the reactants to bring in a total of 6 hydrogens in the reactants as well. Here it's asking us to check the balance of atoms in the following equations. So number 1 asks how many hydrogen atoms in the product. So we only have 1 source of hydrogen in the products, and that's from H2O. That 4 gets distributed to the H and the O, so it's 4 times 2, which is 8 hydrogens in the products. Number 2 asks for the number of oxygen atoms in the reactants. And so the only source of oxygen in the reactants is Fe3O4. And so it's 4 oxygens in that molecule, in that compound. So it's only 4 for number 2. And then number 3, it says number of Fe atoms or iron atoms in the reactant. So we only have 1 source of iron atoms. And so we're just using the subscript, which is a 3 for 3 iron atoms being. So here you can see what it was doing. It was just using the number 1, using combination of the coefficient and the subscript, and then for 2 and 3, you just had to use these subscripts in order to figure this out. We went over a little bit of polyatomics in the last chapter, and so we will see chemical equations using polyatomics. And so with polyatomics, we want to just keep the polyatomics together. Don't break them up unless it's absolutely necessary, and we probably won't have to deal with that much in this class. So if you see a polyatomic, if you see a phosphate, if you see an ammonium, if you see a sulfate or a nitrate, if you see anything with parentheses, just keep that part together. Don't break it up until it's absolutely necessary. And like I said, it probably will not be dealt with in this class. So in this balanced reaction, you see that we have sodium phosphate and reacting with magnesium chloride, and it's going to make magnesium phosphate and sodium chloride. And so notice how they keep that PO4 group together. That phosphate group stays together, so we're not going to break it up. And so when we balance them together, as you can see in the table, it keeps that phosphate together. That PO4 3- is staying together, and so just kind of treat it as an element, as we've done in the previous questions. So if we're going to balance this out, we're going to write out our chemical equation, and so you write out all the parts. Then in step 2, again, we're going to write out a chart and figure out how many of each of the atoms or polyatomics that we have. And so sodium is only in one compound, and so there's on the reactant, so we have 3 sodiums, and we have in the reactants and 1 on the products. In the phosphate, the PO4 group, we have 1 of those on the left of the reactants, and we have 3 of them, 2 of them on the right. So that 2 after the parentheses belongs to only the phosphate, so the PO4. So we have 2 of those phosphates groups. On the left side, we have 1 magnesium with magnesium chloride, and then we have 3 magnesiums in the magnesium phosphate. So that 3 after the Mg belongs to the magnesium. And then we have 2 chlorines in the reactants and 1 on the product. So now we have to balance. So in our balancing, we're going to have to use coefficients. And so you could start from a number of places. What I would have done was I would have could start a number of places, I guess, but you can start off with the, in this case, I guess the easiest way would be the magnesium. So we have 3 magnesiums in the products, and so you would need 3 magnesiums in the reactants. And so that would mean you need to add a 3 in front of the MgCl2. And so when you do that, that brings up a total of 6 chlorines in the reactants. And so you need to get 6 chlorines in the products. And so in order to do that, you need to add a 6 in front of the NaCl. So when you add a 6 in front of the NaCl, you get 6 chlorines, but then you also get 6 sodiums. You need to go back and change the sodiums in the reactants. And so you have 3 sodiums in the reactants, and so you need to add a 2 in front of that Na to bring a total of 6 sodiums in the reactants. And so when you add that 2 in front of the Na3PO4, that means you have 2 phosphate groups in the reactants, and you indeed already have 2 phosphate groups in the products in the Mg3PO4 too. And so we are now balanced. So as you can kind of see, it's kind of a chain reaction. If you change one thing, then you're going to have to repeatedly change other coefficients. And so it's just a matter of, I guess, trying to find where to start. And so here it's asking us to balance out these balance out the reactants and products. And we have a set of choices. All right, and so in number 1, we have Fe2O3 plus C goes to Fe plus CO2. One thing that when you get practice and notice these things and do them after a while, if you see an odd number of an atom on one side and an even number of that same atom on the other side, you probably want to multiply that odd number by 2 to make it even. So what I mean here is that we have Fe2O3 on the left-hand side. So we have 3 oxygens on the left, and we have 2 on the right. So the first thing you want to do is multiply that, put a 2 in front of the Fe2O3 to make it even. All right, so when we do that, we end up with 4 irons and 6 oxygens on the left-hand side in the reactants. And so then, if we have 6 oxygen on the left, then we need to have 6 oxygen on the right. So that means we need to add a 3 in front of the CO2. And so when we do that, our oxygens are now balanced, but now we have 3 carbons on the right and only 1 on the left. So that means we need to add a 3 in front of the carbon on the left, the carbon that's all by itself. And then we also need to balance out the iron, Fe. So we had already added a 2 in front of the Fe2O3. So that means we have 4 total ions on the left. So we need 4 on the right. So we need to add a 4 in front of the Fe. So our answer is going to be B. For number 2. We see that we have one we have 1 aluminum, 1 iron, and 1 oxygen on the left, and 1 iron, 2 aluminums, and 3 oxygens on the right. So you can start off by balancing out your aluminums or your oxygens, and so your aluminum, you can put a 2 in front of the Al on the left, and you can just keep the 1 in front of the Al2O3. Then you can put a 3 in front of the FeO, so you can have 3 oxygens on the left and 3 oxygens on the right. And so if you have 3 oxygens on the left, then you need to put a 3 in front of the Fe on the right side. So it's going to be choice A, 2, 3, 3, 1. And then lastly, number 3. Here we have a sulfate group, an SO4, so we want to keep that SO4 together and kind of treat it together. So here we see that we have 1 sulfate group on the left and 3 on the right. So that probably means that we need to add a 3 in front of the H2SO4. So when we do that, that means we end up with 6 hydrogens on the left, and we need 6 on the right. So then we'll need to add a 3 in front of the H2 in the products. So our hydrogens are balanced, our sulfates are balanced. Now we need to balance out our aluminums. We have 2 in the products and 1 in the reactants. So we need to add a 2 in front of the aluminum and the reactants. And so that brings it to 2, 3, 1, 3. So choice B. All right, and here you go. And it doesn't really do them out for us here, but you can work them out and see, and work them out for yourself, do it individually, and then see if it works out in the same way. So in the next part, we'll talk about types of chemical reactions. There's several types of chemical reactions, and you'll have to be able to identify the different types. So we have combination reactions, decomposition, single replacement, double replacement, and combustion reactions. And so we're going to look at these different types and see what they are about. So I guess the slide is a little bit messed up, but here it says a combination reaction is when we have 2 or more elements or simple compounds combined to form one product. And so whatever blocked out should be products. And so here's just a little example of different types. And so we have magnesium and oxygen coming together to form magnesium oxide. We have sodium and chlorine coming together to make sodium chloride. Here we have sulfur trioxide and water to make sulfuric acid. And so these are all starting off with more than one reactant, and you're combining them to make only one product. So combination, you're combining more than one thing to make just one. And so here's just an example of magnesium oxide. And so it's a very popular experiment where you have magnesium ribbon, you put it on fire, reacts with oxygen, and you make magnesium oxide as your product. And so here you're starting off with magnesium and oxygen, and you make magnesium oxide. So more than one product combining, more than one reactant combining to make just one product. Decomposition, so when something decomposes, it breaks down, it breaks apart. And so in a decomposition reaction, you start off with one substance, and it's going to break down into more than one substance. And so you see a couple of examples here. We have mercury oxide breaking apart into mercury and oxygen. We have potassium chlorate, breaking down to potassium chloride and oxygen. And so you're starting off with one substance and breaking apart into more than one substance. So here you can see both the visual and the chemical reaction or chemical equation of the decomposition of mercury oxide. So when you have mercury oxide and you heat it up, you can see it's being heated because it has that triangle or the delta above the arrow. And so when it's heated, it's going to break down and you can produce just mercury atoms, a mercury liquid, and oxygen gas. And so you can see um, the change, the chemical changes occurring in the test tube. And so you're starting off with one reactant and breaking down to multiple products. Single replacement is when you have one element just replacing an element in the other reactant. And so it's just like a little, you're doing a single switch. And so here we have zinc reacting with hydrochloric acid. And so in this single replacement reaction, the zinc takes the place of the hydrogen. And so they're just doing a single swap. So you have an element that's by itself taking the place of an element that's in a compound. All right, same thing with iron and copper sulfate. And so the iron is by itself and it's replacing the copper that's in a compound. So it's just doing a single replacement of a single element within an element in the compound. And so here's the zinc and hydrochloric acid example, and I'm kind of showing you the what happens. And so when you put a zinc strip in hydrochloric acid, you see the bubbling going on. You see that the zinc metal is basically dissolving and breaking apart, and those releasing hydrogen gas, and then the zinc chloride, the product's going to stay in solution. And so you see an obvious change in the materials. You see a chemical change, and so the chemical equation is written down there. And so you see that the zinc is just replacing that hydrogen in the hydrochloric acid compound. Here we have a double replacement, and so here in a double replacement, you're going to have elements or atoms that are both in compounds switching or exchanging places or replacing each other. So in single replacement, there was one element by itself. In double replacement, you have both atoms in compounds and they're swapping places. And so here you see the silver nitrate reacting with sodium chloride. And so the silver and the sodium are swapping places, they're exchanging. And so we end up with silver chloride and sodium nitrate. And so the main difference between single and double replacement, you have an element by itself. Double replacement, you have both materials, both reactants are compounds. And so here you see the reaction of sodium sulfate and barium chloride. And when they react with each other, when you add them together, you make barium sulfate, which precipitates out of solution, and so it becomes solid. And so you see that solid being made in the beaker there, and then you have the sodium chloride, which stays in solution, so the salt stays dissolved. And then lastly, we have combustion reaction. So that's when we have a carbon-containing compound that's being burned in the presence of oxygen. And so when you do that, you're going to produce carbon dioxide and water as your products. And as many of you know, when you burn them, you are going to produce some energy, usually in the form of heat. And so this is just an example showing you propane. And propane, when it's lighted up, it reacts with the oxygen, and it's going to produce carbon dioxide and water. And so here's just a nice little summary of the different reactions. Gives you, the general um, formula, and then gives you some examples of the different types of reactions. So here it's asking us to identify these as either combination or decomposition. So in 1, we have 2 reactants combining together to form one product. So that's combination. In 2, we have 1 reactant breaking apart or decomposing into more than one product. So that's going to be decomposition. And then lastly, number 3, similar to number 1, we have more than one reactant coming together to form one single product, so combination. Now it's asking us to classify these as single or double replacement reactions. So the easiest way to do this is if you have an element by itself in the reactant, it's going to be single replacement. So 1 and 3 both have an element by itself, and it's replacing the atom in the compound. And so if it has an element by itself, that's going to be single replacement. And so then number 2, you have 2 compounds that are swapping atoms, and so that's going to be double replacement for number 2. And so there you see it. And so now we have all the different types, so we have to figure out what each one of these are. And so number 1, we have two materials combining to form one, and so that is going to be, number 1 is going to be combination. Number 2, we have an element in a compound making another compound in a different element, but we have elements by themselves that were swapping places. The mercury, the Hg, and the hydrogen, the H, are trading places, so that one's going to be single replacement. Number 3, you have a swapping of the Pb, the lead, with the potassium, the K. Both of them are both in compounds, so that's going to be double replacement. 4, you have 1 reactant, and they're decomposing and breaking apart into 2, so that's going to be decomposition. And then number 5, we have a carbon-containing compound reacting with oxygen to produce carbon dioxide and water and energy. So that one is combination for number 5. So there it's written out for us. And so now we're going to talk about another special type of reaction called an oxidation reduction reaction, or sometimes called redox reactions. And so when we have oxidation and reduction reactions, there's going to be a transfer of electrons. So there's going to be one atom or element that's going to be gaining electrons, and then equally you'll have an atom or element losing electrons. So there's going to be a balance of these electrons being transferred from one another. So some are going to lose them, some are going to gain them. And these are seen in a lot of different places. They have those going on within our bodies. We have, another popular one is when iron rust. That's a redox reaction. And so we're going to look at these reactions and see and try to determine which ones are gaining and losing electrons and how many are being gained and lost and things of that nature. So one tip that you can remember, help you remember which is what oxidation means and what reduction means, is oil rig. So oxidation is losing, reduction is gaining. So when oxidation takes place, you are losing electrons. When reduction takes place, you are gaining electrons. And so oxidation, when you're losing electrons, you're losing that negative of the electrons. So you're going to become positive. When you go through reduction, you're gaining electrons. So you're going to become negative, or you're going to become less positive. So in the oxidation of zinc, you see that zinc starts off at 0 charge, and if it's being oxidized, it's going to lose 2 negative charges. So if you have 2 negatives being lost in the zinc, you're going to have 2 positives remaining, and that balances out. So you want to make sure your charges are balanced. You have 0 charge on the left, and you have a +2 on the zinc on the right, and 2 negatives on the electrons on the right. So the +2 balances out the -2. And so you have 0 on the right. So 0 on the left, 0 on the right. When you have reduction, here we have copper ions, copper 2+. It's gaining 2 electrons. And so you're going to make copper metal. And so you have balance of charges. You have Cu +2. You have +2 on the copper and 2 negatives on the electrons. So +2 and -2, you get 0 on the left, and you have 0 charge on the right. So you want to make sure those things are balanced. Those charges are balanced. So oil rig, oxidation is losing electrons, reduction is gaining electrons. And so in these reactions, you'll have one element such as element A is going to give its electrons. It's going to lose its electron to B. It's going to give it to B. And so if A is losing its electrons, oxidation is losing, it's oxidizing, and B is gaining electrons. So rig is reduction is gaining. So B would be gaining electrons. And so reduction, you can see that you go less positive and more negative. So your charge is becoming less and less and less. Oxidation is going to be more and more positive. Reduction is more negative. Oxidation more positive. So if we look at this reaction of calcium and sulfur producing calcium sulfide, if there is 0 charge of if there's 0 charge on an element, you won't see any plus or negative around that element as a superscript. So you have Ca solid, so that means calcium has 0 charge as in a reactant. But when calcium's with sulfur in the product, calcium sulfide, we remember that sulfur is in group 6A when it wants to gain 2 electrons, and calcium is in group 2 and likes to lose 2 electrons. So calcium and calcium sulfide in the CaS is going to be +2 charge. So that means calcium went from 0 charge in the calcium 0, or calcium solid, and it went to calcium +2. And so in order to do that, it has to lose 2 electrons. In the reactants, in sulfur, again, when it's by itself, it's going to have a 0 charge. And when it's in its product of calcium sulfide, being in group 6A, it likes to gain 2 electrons. And so it went from 0 charge to -2 charge. So in order to do that, it's going to gain 2 electrons. And so it's being reduced. It's gaining. Reduction is gaining. And so so we also see that we have, calcium is losing 2 electrons and sulfur is gaining 2 electrons, and they're balanced in that respect as well. And so here it just kind of works it out for you. When you have these redox reactions, you want to make sure that those electrons are balanced. You want to make sure that the number of electrons that are being lost are equal to the number of electrons being gained. Otherwise, it doesn't really make so much sense. You're being able to just let anything happen without any type of rules that go along with it. So here you need to have the balance of these charges. If you're going to gain so many electrons, they need to come from somewhere. So something has to lose that same number of electrons. Here we see another example of when zinc is added to copper sulfate. Zinc undergoes oxidation and then copper undergoes reduction. And so when you have zinc metal in the copper sulfate, zinc is going to be, remember, oxidation is losing, so zinc's going to lose electrons, and so zinc is going to dissolve into solution. Copper is going to gain. It's going to be reduced. Reduction is gaining. And so copper is going to come out of solution. So when you dip that zinc strip into the copper sulfate, you see that the copper deposits onto the zinc because the copper gained electrons and becomes solid. And that zinc is going to dissolve into the solution. And so here we have a single replacement as well. And here's just kind of a picture showing what's going on. Is that copper comes by that zinc, and then that zinc is going to give 2 electrons to the copper, and then the copper is going to deposit onto that strip. And then that zinc that gave up its electrons goes into the solution. So here we need to identify each of these as either an oxidation or reduction reaction. So oxidation is losing, reduction is gaining. So here we see that tin is losing. Tin is losing, and so that's going to be oil. Oxidation is losing. Number 2, we are gaining electrons. So reduction is gaining. So 2 is gaining, reduction. 3 is gaining, reduction. And here you go. One trend that you'll notice is that when metals are in their elemental form, in their solid form, they are more likely to go through oxidation. They're more likely to lose electrons. Non-metals in their elemental form are more often going to be reduced. They're going to gain electrons. All right, and so that kind of goes with, metals like to lose electrons, and non-metals like to gain electrons. So metals like to become positive charge, non-metals like to become negative charge. So it kind of ties into our last chapter. Here it goes into talking about what happens when silver and chlorine react with light. And so here it's just asking us what reactant is oxidized, what reactant is being reduced. And so silver is going from positive to 0 charge, so it's going to have to gain a negative charge to do that. So silver is gaining electrons, so reduction is gaining. So silver is answer to number 2. The reactant Ag plus is gaining. And here the reactant being oxidized, Cl minus, oil oxidation is losing. And so here you're going from a negative charge to a 0 charge. So you're losing that negative. So you're losing that electron. So chlorine minus, Cl minus is losing and is being oxidized. And so that's what we see here. And it gives you the balanced, oxidation and reduction reactions. Here again, it's asking us what are being oxidized and what are being reduced. So here we see magnesium is going from a 0 to a positive 2. So it's losing its negative charge. So oxidation is losing. All right, so magnesium is being oxidized, and then H plus is going from plus to 0. So it's gaining electrons. So reduction is gaining. So H plus is gaining. In number 2, all right, this one, aluminum on the reactants is 0 charge, and bromine is 0 charge in the reactants. Then we have to figure out our charges on the right. So bromine, because it's a 7A element, is going to be a negative 1 charge. And aluminum is group 3A, and so it wants to be a positive 3 charge. And so aluminum is going from 0 to positive 3. Bromine is going from 0 to negative 1. So aluminum is losing its electrons. It's losing its negatives. So oxidation is losing. So aluminum is oxidized. And bromine, it goes from 0 to minus 1. So reduction is gaining. It's gaining negative charge. So bromine is being reduced. And so that's what we kind of see here. All right, magnesium is going from 0 charge to +2 charge, so it had to lose 2 electrons. And then hydrogens had to go from positive to 0, so it had to gain negative charges, so it had to be reduced. And then 2, aluminum is being oxidized, and so it's going from a 0 charge to a positive 3 charge, so it's losing its negatives, and so it's being oxidized. And then bromine is going from 0 to a negative charge, so it's gaining negatives, it's being reduced. Typically in biological systems, what occurs is either the gain or loss of hydrogens and oxygens. And so the word oxidation means that it's more likely to gain oxygen. And so in biological systems, when substances and materials are being oxidized, they're going to be gaining an oxygen and typically lose a hydrogen. And then just the opposite for reduction. When they're being reduced, they're losing an oxygen or they'll be gaining hydrogens. And so one example here is when some compounds that we have this FAD and FADH2. Usually you'll see those in cellular respiration. And so here the coenzyme FAD is going to be reduced by gaining 2 hydrogens, and then the other original biological molecule is going to lose its hydrogens, and so when it loses its hydrogen, it's going to be oxidized. And so this is just a chart, that kind of table that kind of just summarizes that in biological systems. So that brings us to 6.4, talking about the unit of the mole. So many times we use certain terms to describe a certain number of quantities. And so, we use the word dozen to talk about the number 12, or a case with 24. When we talk about paper, a ream of paper is 500 sheets. So we use a similar unit type of system in chemistry, and we use that as the mole. So a mole is the counting unit used in science or chemistry. And so the mole is based off of carbon-12, and so it's just the number of particles there are, number of carbon atoms there is in 12 grams of carbon-12. That's nothing you need to memorize or anything like that, just kind of telling you where it comes from. But what you do need to know is that number 6.02 times 10 to the 23rd. And so I'm not going to ask you to memorize that. I'll give that to you if you ever need it on a test or a quiz. But that's Avogadro's number. And so that's just the number of atoms that was indeed found in 12 grams of carbon-12. And so that number, the Avogadro's number, can represent a mole of any type of material. All right, so it tells you a mole of carbon is 6.02 times 10 to the 23rd carbon atoms. We have a mole of hydrogen we have a mole of water. You have a mole of 6.02 times 10 to the 23rd molecules of water. You have a mole of potato chips. You have 6.02 times 10 to the 23rd potato chips. So it's just a number that's used to represent how many you have of something. All right, and so here you see, again, it's a very large number, and so that's why we use the scientific notation of that number. So for the mole, if you have a covalent compound, it tells you how many of each of those, how many molecules you have of that compound. So if you have 1 mole of carbon dioxide, you have 6.02 times 10 to the 23rd molecules of carbon dioxide. If you have 1 mole Water, you have 6.02 times 10 to the 23rd molecules of water. If you have an ionic compound, it tells you how many you have of the compound, or the compound together. So for 1 mole of NaCl, you have 6.02 times 10 to the 23rd um, NaCl compounds, or formula units is what they like to call them. If you have 1 mole of potassium sulfate, you have 6.02 times 10 to the 23rd formula units of potassium sulfate. So it's just different terminology sometimes used in covalent versus ionic compounds. And so again, just showing you a table of the relationship between mole and the number that they're talking about. And so sometimes very often you have to use conversion factors using Avogadro's number. And so you can use it in either way. You can have 6.02 times 10 to the 23rd parts per mole, or 1 mole per 6.02 times 10 to the 23rd parts. So you can use either one depending on what you are looking to do with it. And so we'll be showing that in this chapter. So when you're trying to figure out how much material you have, then you first want to figure out, like we've done, is figure out what you have and figure out what you need to get. So, just writing out where you're starting, where you're going to end up with. Then you can write out a plan. Is there going to be an intermediate step, a middle step to get to where you're going, or is it going to be just a direct conversion? And then once you figure out what you need to do, then you can use Avogadro's number, write out all those conversion factors, and then set up the problem to calculate it. So here's asking how many copper atoms are in 0.5 moles of copper. And so we have, the moles. That's what we're given. We need to get to number of atoms. So we're going to go from moles to atoms. So we've got to use Avogadro's number. So we're going to use if we're trying to go from moles to atoms, we want the moles to cancel out. So we want the moles in our conversion factor to be in the denominator. So the moles will cancel out. So we want to use the first one, 6.02 times 10 to the 23rd copper atoms per mole of copper. So when we set it up, we can see that the moles cancel out and we're left with copper atoms. We just do the numbers, the math, and we get our final answer of 3 times 10 to the 23rd copper atoms. The next one is asking how many moles of carbon dioxide are in 2.50 times 10 to the 24th molecules of carbon dioxide. So in this one, we're doing just the opposite. We're given molecules, we need to go to moles. So we're going to start with molecules. We've got to use Avogadro's number to get to moles. So we're going to use the opposite conversion factor. We want our molecules to cancel out. So we want molecules, or the parts, to be on the bottom and mole on the top, because we want to keep the moles. That's what we're trying to figure out, is the number of moles. So we're going to use 1 mole of carbon dioxide per 6.02 times 10 to the 23rd molecules of carbon dioxide. And so when we do that, our molecules cancel out, and we do our math, and we get 4.15 moles of carbon dioxide. So the subscripts, remember, we still have subscripts in compounds, and so if we're looking at figuring out how many moles of each of the atoms are in a compound, that subscript gets distributed to each of those moles. So if you have 1 mole of aspirin, C9H8O4, then that 9 gets distributed to that carbon. So you have 1 mole of the whole compound, but in one compound you have 9 carbons. So you have 9 moles of carbon. In 1 mole of aspirin, you're going to have 8 moles of hydrogen, because if you have 1 molecule of aspirin, you have 8 atoms of hydrogen. So if you have 1 mole of aspirin, you're going to have 8 moles of hydrogen. And similarly, same thing with oxygen. If you have 4 atoms of oxygen in 1 molecule of aspirin, it means you have to have 4 moles of oxygen if you have 4 moles of aspirin, 1 mole of aspirin. So the subscripts in a chemical formula relate to how many of that particular atom you have in the compound. And so that will also relate to how many moles you have of that atom in a mole of the material. And so you can use that that relationship and create a conversion factor, and depending on what you are trying to convert to or from, you can use either the moles of the atom on the numerator, or you can put the moles of the compound in the numerator. So just depending on what you're trying to set up. And so this one just kind of shows you all the possible setups for both the carbon, hydrogen, and oxygen atoms. So when you're trying to calculate the mass, you again, with our guide, you're going to state what you're given, state what you need, write out a plan of what you're going to do. Where are you going to go? Are they in the intermediate steps? Write out any of the conversion factors that you need to use, and then set it up and calculate it. So here it's asking us to how many moles of carbon are present in 2.3 moles of propyl acetate, C5H10O2. All right, and so you state that you're given 2.3 moles of the propyl acetate and that you are looking to find how many moles of carbon. So you're going to just use the subscripts in the compound to figure out, to convert the moles of C5H10O2 to moles of C. And so in 1 mole of C5H10O2, you have 5 moles of carbon. And so in this case, you want the moles of C5H10O2 to cancel out. So you want that in the denominator, and you want moles of C in the numerator. And so here you see that being set up. And so our moles of the propyl acetate cancel out. And so you're left with 2.3 times 5 moles of C is equal to 12 moles of C. Now it's asking how many oxygen atoms are in 0.150 moles of aspirin, which is C9H8O4. And so we're given how many moles of aspirin we have, and now we need to figure out how many atoms of oxygen we have. So we need to first start with moles of aspirin, then using subscript to get moles of oxygen, and then using Avogadro's number, we're going to convert to atoms of oxygen. And so the qualities that we're trying to figure out, we want to convert our moles of aspirin to moles of oxygen. So we want to have the moles of aspirin cancel out. So we want to use the 4 moles of oxygen per mole of aspirin. And then we want our moles of oxygen to cancel out and be left with oxygen atoms. So we want to use the 6.02 times 10 to the 23rd oxygen atoms per 1 mole of oxygen conversion factor. So both of them are on the right hand side. So we set it up, and so our moles of aspirin cancel out, our moles of oxygen cancel out, and so we're left with 0.15 times 4 times 6.02 times 10 to the 23rd oxygen atoms is equal to 3.61 times 10 to the 23rd oxygen atoms. Now this brings up the concept of molar mass. So molar mass is just the mass of 1 mole of a material or a substance. And so we may be the mass of just an atom by itself, or for the compound. And so in these examples, in this type of questions, we have to use the masses, the atomic masses that are molar masses are given on the periodic table. And so, and here they have the examples of silver, carbon, and sulfur. So we've been using the atomic numbers, but there's also that larger number that's on the bottom below the numbers that are the molar masses. And so those molar masses, or atomic masses, state that in 1 mole of that atom, that is how many grams of that of those atoms you have. So in silver has a molar mass of 107.9 grams. So that means in 1 mole of silver atoms, the silver atoms will weigh or have a mass of 107.9 grams. For carbon, if you have 1 mole of carbon atoms, it's going to have a mass of 12.01 grams. If you have a mass of, if you have 1 mole of sulfur, it's going to have a mass of 32.07 grams of sulfur. So in these calculations, you need to obtain the molar mass of the elements and then multiply the molar masses by the number of moles in the chemical formula to figure out the molar mass of that particular element. So here we have calcium chloride, and it's asking us to calculate the molar mass of calcium chloride. So we're given, we have CaCl2, so that means we have 1 calcium and 2 chlorines. So we want to first obtain the molar mass of each element. We have look on the periodic table, and we find that calcium has a molar mass of 40.1 grams per mole. Look at chlorine, it has a molar mass of 35.5 grams per mole. In CaCl2, you have 1 mole of calcium. All right, we have 1, so we just have to multiply 1 mole of calcium by 40.1 grams per mole, and we get 40.1 grams of calcium. If we have CaCl2, that means we have 2 moles of chlorine and 1 mole of calcium chloride. So we have 2 moles of chlorine, Cl, times 35.5 grams per mole, and that brings it up to 71 grams. And so then all you have to do from there is you just need to add those two numbers together, and you get 111.1 grams for calcium chloride. So calcium chloride has a molar mass of 111.1 grams per mole. Wants us to do the same thing for potassium phosphate. And so here we've given the formula potassium phosphate, K3PO4. So we have 3 moles of potassium, 1 mole of phosphorus, and 4 moles of oxygen. Looking on the periodic table, we have a molar mass of 39.1 grams per mole for potassium, 31.0 grams per mole for phosphorus, and 16.0 grams per mole for oxygen. So having 3 moles of potassium, we need to multiply 3 times 39.1. We have 1 mole of phosphorus, so 1 times 31 is 31 for phosphorus. 4 moles of oxygen times 16 is equal to 64 grams of oxygen. And so now you just have to add those 3 numbers together, and you get a molar mass of 212.3 grams per mole of potassium phosphate. And so now it wants us to figure out what is the molar mass of Prozac. So C17H18F3NO. And so what you really need to do is you need to multiply the molar masses of the periodic table times the subscripts. So for carbon, you're going to multiply 12.01 times 17. For hydrogen, you're going to multiply 18 times 1. For fluorine, you're going to multiply 3 times 19. For nitrogen, you're going to multiply 1 times 15. And for oxygen, it's going to be 1 times 16. And then you add them all together. All right, so we have our problem. We have to, we know how many of each of these atoms we have. We know these molar masses based on the periodic table. We multiply the moles of the subscripts by the molar masses, and then we add all together here. And when we add them all together, we get 309 grams per mole. And so this is just showing you another example of general idea of when you have a higher molar mass, you generally have more of that material when you have it together. So just showing you the way showing you what 1 mole of material can look like. And so it can look like a lot of different amounts based on different type of material you could have. So we can use these conversion factors of molar mass. We can use them either way. We can have grams per mole or moles per gram, depending on what you're trying to do with those molar quantities. And so when we're using these molar masses in our calculations, we're following the same steps. State what we're given, state what you need to get. You're going to write out your plan, what you're going to go and use. Then write out your conversion factors and then set it up and find your final product. So here's asking how many moles are present in 65.1 gram sample of KCl. So we are given that we have 65.1 grams of potassium chloride. And so to go from grams to moles, we need to use our molar mass. So we just calculate our molar masses like we've done in the past. We have 1 potassium, which has a molar mass of 39.1, and 1 Cl, which is 35.5. And so when you add those two together, you get 74.6. So in 1 mole of potassium chloride, it has a mass of 74.6 grams. And so since we're trying to go to moles, we want the moles to stay and the grams to cancel out. And so we end up dividing 65.1 by 74.6. Grams cancel out. We're left with moles, and we get 0.873 moles of potassium chloride. If we have acetic acid is a main contributor in vinegar. And when we have if it wants us to calculate how many moles we have of acetic acid in a 25.8 gram sample of acetic acid. So we are given the grams, we need to go to moles. And so in order to do that, we have to use this molar mass. In order to go from grams to moles, we want our grams to cancel out and our moles to be left. So we want the moles to be on top and our grams to be on the bottom. And if we calculate out the molar mass, carbon has a molar mass of 12.01, so we have 2 of those, so 2 times 12, which is 24. Hydrogen has a molar mass of 1, so 12. We had 24 from carbon, 4 from hydrogen, so that brings it up to 28. And then we have 2 oxygens. Each oxygen has a molar mass of 16. We have 2 of those, so that's 32. So we have 28 plus 32, which is equal to 60. And so 60 grams per mole. So we want our grams to cancel out. So it's going to be 1 mole divided by 60 grams that we use. And so 25.8 grams divided by 60 grams, we're left with 0.43 moles of acetic acid. And so this is just kind of a little chart that shows, how you can go from one given to another, and kind of shows you what you will need to use in order to use to go to where you're looking to get to. So here's another one, and we have calcium carbonate. If we have 0.32 moles of calcium carbonate, how many moles are present? So in this case, we need to go from moles to grams. And so in order to go from moles to grams, we need to use molar mass. So we have to calculate the molar mass. 12 is the molar mass of carbon. We have 1 carbon. We have 3 oxygens, which is 16. So it's going to be 12 plus 3 times 16, which is 48. So 12 plus 48 is 60, plus calcium, which is a molar mass of 40.1. So 60 plus 40.1 is 100.1 grams per mole. We want to go from moles to grams. So we want our moles to cancel out. So we want moles to be in the denominator. grams in the numerator. So 101.1 grams per mole is what we want to use. So we set it up, 0.32 times 100.1 grams per mole, we get 32 grams of calcium carbonate. And so now we'll look at mole relationships and chemical equations. And so this is a big thing, a very important part of the chapter. And so in this part, we're going to be going from comparing the amounts of reactants to the amounts of products. And the key thing is by using the mole relationships. And so if you ever want to go from reactants to products or products to reactants, it's important that you're comparing by using the number of moles. So we start off by just mentioning the law of conservation of mass. So law of conservation of mass. So conservation just means that it's going to be conserved. You're not going to lose it. You're not going to gain it. So law of conservation of mass is basically you cannot create or destroy matter. It's going to just you're going to end up with the same amount of material that you started with. So the total mass of your products is going to equal the total mass of your reactants. You're not going to lose any mass anywhere. You're not going to magically make matter in any way. So it's got to be equal. And so if you are to make a reaction of silver and sulfur to make silver sulfide, silver 1 sulfide, then if you start off with 2 moles of silver, which would be 215.8 grams, and 1 mole of sulfur, which would be 32.1 grams, you would have a total mass of reactants of 247.9 grams. So if that reaction was to go to completion, you would make a total mass of 247.9 grams of silver sulfide. So here's just kind of showing you the information you can get from the equation. So if you have a balanced equation of 2Ag plus S goes to Ag2S, that means if you have 2 moles of silver atoms, if you have 2 moles of silver and a mole of sulfur, you're going to make 1 mole of silver 1 sulfide. And so using the molar masses, you can calculate the mass of each reactant and each product, and you'll see that the mass of the reactants equals the mass of the products. So if we were to look at the chemical equation of 2 irons plus 3 sulfurs making iron 3 sulfide, then we can just, instead of using atoms, we can just say use moles. So if we have 2 moles of iron plus 3 moles of sulfur makes 1 mole of iron 3 sulfide. So here we see the balanced reaction and what the reactants look like in their natural form and what the product looks like in its natural form. And so when we react all of that iron and all of that sulfur, the total mass of those reactants will equal the total mass of that product of the iron 3 sulfide. So this brings us to the mole factors, or sometimes it's called mole ratios. So what the balanced reaction says is that for every 2 iron atoms we have, we require 3 sulfur atoms. Or if we have 2 moles of iron, we require 3 moles of sulfur. If we have 2 moles of iron, we're going to make 1 mole of iron 3 sulfide. If we have 3 moles of sulfur, we'll produce 1 mole of iron 3 sulfide. And so these are just using that balanced reaction and comparing. If we start off with so much of one material, we can make that only that amount of material. And so and we have to use that in our calculations. So if we have hydrogen reacting with nitrogen to make ammonia, it's asking us to figure out what the mole ratio is, the mole to mole factor. And so using that reaction, it says that we need 3 moles of hydrogen for every 1 mole of nitrogen. So if we have 1 mole of nitrogen, we need 3 moles of hydrogen. So our answer is going to be B. Next one is asking us a mole ratio for NH3 and H2. So here we have the numbers 3 and 2. So that means that if we have 3 moles of hydrogen, we are going to make 2 moles of ammonia. Or if we are going to make 2 moles of ammonia, we require 3 moles of hydrogen. And so our answer is going to be choice B and C are both correct. And so I guess in this one they left off C, but B and C said the same thing, if I recall. So in calculating quantities of a chemical reaction, we need to use these mole ratios. So first, like we have always done, we need to state the given, our given. State what we're given, state what we need to get to. Then we need to write out a plan. What are we going to need to convert from one thing to another? How many steps are there? What are the middle steps? Then number 3 is to write out the conversion factors and molar masses that we're going to need in the equation. And then lastly, we can set it up and solve for what we're looking for. So here it's asking how many moles of carbon dioxide can be produced when we have 2.25 moles of propane C3H8 using the balanced reaction. So we have a combustion reaction here where we start off with 1 mole of propane C3H8, and we are trying to, I should say, we're starting off with 2.25 moles of C3H8, and we're trying to figure out how many moles of carbon dioxide, CO2, are going to be made. So in order to go from moles of C3H8 to moles of CO2, we need to use our mole to mole factor, our mole ratio. And so our 2 possible ratios that we could use is 1 mole of C3H8 per 3 moles of carbon dioxide, or 3 moles of carbon dioxide to 1 mole of C3H8. So since we're going from moles of C3H8, we need the moles of C3H8 to cancel out. And we want our CO2 moles to stay. So we want to use the 3 to 1, 3 moles of CO2 per 1 mole of C3H8 on the right hand side. And so when we do that, we multiply the 2.25 moles of C3H8 by 3, and we get 6.75 moles of carbon dioxide. Now it's asking how many moles of iron are needed for the reaction of 12 moles of oxygen gas. And so again, this is very similar. We're using our mole to mole ratios. And so it says we have 12 moles of oxygen gas. So how many moles of iron do we need? And so we're given moles of oxygen, need to get 2 moles of iron. So then we are going to have to figure out what we're going to need to use. So we're going to use our mole to mole factor, our mole ratio. And so our mole ratio is 4 moles of iron per 3 moles of oxygen, or 3 moles of oxygen per 4 moles of iron. And so we want our moles of oxygen to cancel out and be left with our moles of iron. So we want to use the one on the left, 4 moles of iron per 3 moles of oxygen. And so when we do that, we're going to multiply 12 moles of oxygen by 4 moles of iron, then divide it by 3 moles of oxygen, and we end up with 16 moles of iron. So that's choice C. And then lastly, we can use these mole ratios to figure out the masses of one material to the mass of the other, because we typically don't measure out moles. We have to measure out masses using a balance, so we can figure out how many grams of one material can make how many grams of another, or how many grams we're going to need to make so many grams of the product. And so in order to do that, in order to compare masses of reactants and products, we have to use the middleman of moles. So we have to use our mole ratios and our mole factors to figure out the masses. So moles are going to be our middleman. So if we have acetylene gas, C2H2, that burns, another combustion reaction, if it's asking how many grams of CO2 are going to be produced if we burn 54.6 grams of C2H2. So we're going to have to go from grams of C2H2 to grams of CO2. So again, we're going to have to use the moles as the middleman. So we have to start off with grams of C2H2, convert that to moles of C2H2 by using the molar mass. Then use our mole ratio to get to moles of CO2. Then go back to our grams of CO2 by using molar mass. So a lot of stuff going on here. And so we're just writing out all our different conversion factors. And first we're writing out our, we had to figure out our molar masses. So our molar mass of C2H2 is 26. Because carbon has a mass of 12 grams per mole, and we have two of them, and we have two hydrogens, which has a molar mass of 1, so that's 12 times 2 plus 2 times 1, and so that brings up to 26. Then CO2, carbon has a molar mass of 12, and oxygen has a molar mass of 16. We have two oxygens, so that's 32 from oxygen and 12 from carbon. That's 44 grams per mole for carbon dioxide. And looking at our balanced reaction, it says that if we have 2 moles of acetylene, C2H2, we're going to produce 4 moles of carbon dioxide. So to set it up, we want our grams of C2H2 to cancel out and be left with moles, so we're going to use 54.6 grams divided by 26 grams per mole. Then we want our moles of C2H2 to cancel out to be left with carbon dioxide. So it's 4 moles of carbon dioxide per 2 moles of C2H2. Then to go back to grams, we need to use 44 grams of carbon dioxide per 1 mole. And you see it written out there. And so just make sure you follow your units. It can be very easy to do one small thing wrong and get the whole question wrong. So make sure you follow your units. Make sure that your when you multiply, that the denominator cancel out. Um, just make sure you're following those units. Another example, we need to determine the mass of ammonia and H3 that are formed by using 62.3 grams of nitrogen. And so we have the balanced reaction here. And so we need to go from grams of nitrogen to grams of ammonia. And so we're going to have to use the moles as our middleman. And so we go from grams to nitrogen to moles of nitrogen. We need to use molar mass. Then we can compare moles to moles using the mole ratio. And then going back from moles to grams, we can use our molar mass. And so you need to calculate out the molar masses of both nitrogen and ammonia. And then you also need to use find out your mole ratio. And so it's a 1 to 2 mole ratio. And so here it just shows you the math written out. And just make sure you follow your units. And so we get a final answer of 75.7 grams of ammonia.